Hi, everyone, and welcome to this session on building an open source control plane for data. I'm Shirshanka, CTO and co-founder of Acryl Data. And prior to this, I was at LinkedIn, where I ran data infrastructure for a large team over 10 plus years. And as part of my responsibilities, I was responsible for data ingestion, data management, as well as data privacy. And that led me to create a project called DataHub that has since emerged as the #1 metadata platform. I also am to be found on X Twitter, at Shirshanka. So happy to be here. And today we'll be talking about building an open source control plane for data. But before we get there, let's talk about DataHub. DataHub is an open source metadata platform that enables 3 outcomes: data discovery, data observability, and federated governance. And it does it on top of a high fidelity metadata graph. Acryl is a company that's advancing the DataHub project, and commercially it's known as Acryl Cloud. And the way to conceptualize it is that you have a high fidelity metadata graph that contains all your data assets, your code assets, as well as all the people that are working with your data. And on top of this data graph, you can essentially achieve multiple use cases. You can have really good data discovery, you can have really good data governance, and you can also have really good data quality or data observability. And you can find out more at the homepage of the project, datahubproject.io. And DataHub has, over the last few years, emerged as the #1 open source metadata platform. And one of its biggest strengths, of course, is the fact that it was built at LinkedIn and had a lot of battle-tested scalability and performance tackled head-on in the early years of its formation. But really, a lot of its strengths also emerged in its flexible integration architecture. So it has integrations with, almost 50 components of the data stack. Some of them are modern data stack components, some of them are pre-modern data stack components, some of them are post-modern data stack components. But the reality is, all of the systems that you are working with usually in your data jobs, whether it is operational data stores or streaming data systems or transformation engines or BI tools, odds are DataHub already has an integration with it, or someone in the community is already working on building one. We have a lot of adopters, companies, obviously LinkedIn, but obviously a lot of adopters like Pinterest, Stripe, Peloton, Notion, Optum, all over the stack. We're finding technology companies who are working with data and driving data-driven business decision-making, as well as data-driven products, are finding a lot of use for DataHub as the center of their data strategy. I talk a lot about metadata, and so it's worth kind of looking at what that metadata graph even looks like today in DataHub. Obviously, a lot of the metadata and the data concepts start with the venerable dataset object. It's kind of at the center of the graph, but related to the dataset are other entities like tables and streams and folders and schemas and columns and queries. And then slightly outer from that are data processes and charts and pipelines and dashboards, as well as AI concepts like ML models and features. And then coming in from the business perspective are concepts like glossaries and tags that allow you to give meaning to all of this physical and technical metadata that you're seeing. And then from the person side of the house, from the identity side of the house, you get roles and groups and privileges and things like that. And if you're following the more recent discussions that are happening in data, you're probably familiar with data mesh. You're probably familiar with concepts like the data contracts. Those are also first-class citizens of this metadata graph. So as you might imagine, every single data asset or data asset related concept that is important for data practitioners as well as business users is modeled as part of this metadata graph. And that's sort of the challenge that DataHub has. How do you model all of these different concepts, represent them well, and then allow interesting things to be done on top of it? So you might be wondering, well, all of this is great, Shirshanka. You talked to me about DataHub. It is a great open source project. It's got a bunch of metadata inside it, and it represents it really well. So what does that have to do with the control plane of data? Or am I even in the right session? So let's talk about that by first going through a little bit of a history lesson in just the evolution of data itself. If you've been around for the last decade, unfortunately, I have. You'll have noticed that we had major shifts in data over the last decade. We went from the rallying cry of that last decade was volume, velocity, and variety. So being able to handle larger and larger amounts of data, being able to handle the speed at which data was getting generated and moved through our systems, and then also being able to handle the variety of data that we were producing and consuming. And that led to a ton of innovation. If you look at 2012, this is what the data stack looked like 10 years ago, right? I mean, it seems kind of crowded, but it actually seems very well understood and very well organized if you look at what it looks like today in 2023, right? Just in that visual, it's so clear that we went from something that was somewhat comprehensible to something that seems very complex and extremely fragmented. And that, is our modern data stack. That is what you and I and all the other practitioners in data are dealing with every day. A lot of fragmentation, a lot of different systems that we have ourselves created to handle all of this complexity, all of this challenging evolution that has happened in data. And all of this innovation wasn't for a bad reason, right? A lot of things got much easier, much easier. Data storage, we don't think too much about storing data anymore. You pick one of n blob stores and you're done. Or if your data is streaming, then you pick one of n streaming stores and you're done. Or if your data is kind of an operational system and you want to have low latency queries on it, you pick a NoSQL store or something like that. So data storage, data movement, data querying, data visualization, all these segments have had significant amounts of innovation that have come in. And all of that has actually meant that these problems have gotten easier. Same for orchestrators, same for transformation, same for real-time systems. And as we're seeing with the resurgence in AI, a lot of improvements in AI infrastructure as well. And so that's all great stuff. Like all of this fragmentation, all of this innovation has had a good outcome for all of these different segments. But with all good stories, there is a sad piece that comes along with it. For everything that got easier, a few things got harder or somewhat impossible. Some of these problems didn't even exist before. Data discovery is a good example. We didn't even talk about data discovery 10 years ago because everything was in one system and it was never a problem to figure out where your data is and how it's getting transformed because it was all just in one system. But now that it's spread across hundreds of systems, tens of hundreds of systems sometimes, it has become a new problem that we must grapple with and solve for. Data quality and data management used to be problems that we used to tackle. But again, because of the simplicity of the previous stack, they were somewhat more tractable. We had somewhat better control over these things. But now they've gotten much harder. So let's look at them one by one. Data discovery is something we talk about a lot. DataHub, I talked about it as a metadata platform. That's actually the first problem it went and tackled. And one of the things that earlier systems got wrong with data discovery was really trying to tackle it in somewhat siloed ways. First off, a lot of those existing systems tried to just crawl metadata out of physical systems. And that led to the metadata not being real time, the metadata not being fresh, and that led to a loss of trust. And if you can't trust the system that is giving you visibility into everything else, then why would you even use it? There are a few other things that systems got wrong. Some of these systems over-indexed on data warehouses and said, we're just going to focus on the data warehouse and make sure that you can discover all of the data in your data warehouse. Now, on the surface, that doesn't seem like a bad idea because the data warehouse is indeed where all of the data comes and is then processed. But a lot of data actually lives upstream of that. For every system, every table that's in the data warehouse, there's probably something upstream of it in a streaming system or in an operational system. And if you don't include those in your data discovery process, you realize that you're missing valuable context. Finally, there were a lot of systems that solved data discovery primarily as a aggregation and storage problem. So I aggregate a bunch of metadata, I store it in one place, and then I allow you to query it. But what that missed was, hey, there are systems that need to actually understand how this metadata is changing, because there's perhaps automated things that you need to do when that metadata changed. So for example, a schema might change or a new pipeline might produce data that is bad. You need to be able to understand that that change has happened, and then you need to react to that change instantly in some cases. And if you don't have abilities to do that, then a data discovery solution remains just kind of a static, manual, once in a while system, and that doesn't lead to success. So DataHub actually ended up solving for data discovery using 3 specific principles. The first principle is what we call metadata 360, which is combining technical, operational, and business metadata into one comprehensive graph. And that lets you kind of see not only technical metadata, the business concepts, but also operational metadata in one place. And that gives you kind of a much better picture of the asset that you're working with, or the asset that you're thinking about working with. The second principle that we introduced is called shift left. Shift left is a common practice that is known in other development verticals, but it's, we were the first to apply this to metadata itself. And the idea is that just like one of the biggest problems you face with data discovery or metadata in general is that metadata is sometimes not accurate. And the reason it's not accurate is because you are relying on your data consumers to populate it by perhaps going to the UI and fixing documentation or writing net new documentation. And we all know that that doesn't work, right? We've got decades of experience as software engineers to realize that documentation of code and artifacts that are technical is best left in the technical tool itself. So when you're creating new data assets, when you're producing new data assets, that's the right place to actually document it. And that's what we call shift left, being able to declare and collect metadata at source. So perhaps you're checking in an Avro schema or a protobuf schema. You should just write documentation for that asset right there. Perhaps you're checking in a DBT model. You should assign documentation and other kinds of attributes to it right there. In many of these systems, they already have support for these kind of extensions. So you don't even need to repeat yourself twice. All you have to do is map those concepts into the metadata platform. And then finally, active metadata, or the ability to work on real-time streaming metadata. This allows you to inject metadata into the operational plane. We'll see a lot of use cases later in the talk today about that. But the idea is that if metadata is free-flowing and it's connected up to live systems, then you can make much more use of this metadata in a programmatic context versus just in a human context. And that leads to your metadata being trustworthy and your metadata actually being usable. For example, you can know right now whether this table exists in your data warehouse, whether it was ingested in the last 30 minutes, and whether it has had data quality scores produced for it in the last 20 minutes. And if you have that kind of real-time understanding of your asset, you can actually programmatically decide whether to take action on that asset, whether it's trustworthy, whether you can use it or not, right away, without having to wait for a human to do some understanding before figuring that out. So it just opens up a ton of use cases. So this is what the DataHub architecture looks like. It's literally a consequence of those kind of principles applied to designing this system. On the left, you'll see all of the data sources that you're probably familiar with. You might be an Airflow-heavy system, or a data lake-heavy system, or a Spark-based system, or you could have Snowflake, BigQuery, Great Expectations, and even GitHub. And all of these systems, essentially, anytime they consume or produce data, they're able to produce events out into DataHub. In some cases, DataHub itself has connectors that can connect out to these systems and pull metadata out and push it out into DataHub as a stream. So essentially, you've got a continuous stream of metadata emerging from your data plane that's going into DataHub. DataHub is recording it, storing it into a graph, and continuously refining and enabling monitoring of the graph itself. On the other side of the graph lives the data discovery application. And that's what a business user or a technical user would be using to come in and search for the revenue dashboard, or to search for a Spark job, or to search for a MySQL table, and then understand how it relates to all of these other concepts. But it's not just the human-facing application. There's also automated actions that are getting driven off of the same metadata graph. For example, perhaps a schema evolved in a backwards incompatible manner, and you want to raise an alert or send a notification to all of the downstream users that, hey, this table has evolved in a backwards incompatible manner, and your assets might be affected. Or perhaps a new asset has landed in the data ecosystem, and it has been classified as being PII, and you want to automatically lock down access control. Or perhaps you need to raise a service ticket for a data steward or a security officer to come in and take a look. All of these automated actions are available off of that same chain stream that I talked about, the metadata chain stream. So this, in a nutshell, is the DataHub architecture. It allows for free-flowing metadata to come into the system, to get canonicalized and harmonized, and then to power both human-facing experiences as well as automation experiences. And since I talked a lot about the human-facing application, this is what it looks like. This is kind of the homepage. You come in, you search for stuff. You can either explore or just straight up search. When you search for stuff, you get back a lot of assets that matched. Those assets can be across tables, dashboards, AI assets, and things like that. And then you get a standard search and filtered search experience where you can then drill down further into the things that you care about. So perhaps you care about only the assets that have been used the most or the most relevant, or perhaps you care about the assets that are owned by your team. You get all of that capability in kind of this unified search and browse view. Once you do that, and once you've found an asset that you perhaps want to use in your analysis or want to investigate further, you get into the entity profile page where you can get even more details. You can understand the schema, you can look at its documentation, you can look at its lineage, as well as many other things. Lineage obviously is a very important facet of this product because it allows you to understand how data flows from point A to point B, but it also allows you to understand what happens if you change one thing. So perhaps I want to change one column in a table I own. Who all does it impact? Who all might get affected? What all systems are downstream of me? And if you invert it, perhaps I am a business user and I'm just receiving a dashboard. I come in and I want to understand, how is this dashboard getting produced? What tables is this data getting sourced from? And are they actually using the right calculation when they're producing this dashboard? I can get all of that insight just by starting from the lineage viewer. And then this is something that Stripe actually contributed. They're basically taking DataHub and using it for operational insights, for actually doing pipeline observability. So they've taken their Airflow jobs and their Airflow tasks, and they pipe all of that metadata into DataHub, and they're able to see timeliness reports of individual data sets and individual pipelines. So you can actually start using it almost as an operational console for data. So these are all the different kind of ways in which the data discovery problem is being solved. So I think we've had a lot of problems introduced by all of this data fragmentation, but through projects like DataHub, we're starting to see light at the end of the tunnel. We feel like, okay, we've managed to connect up to all of these different systems. We are able to pull metadata out, and then we're able to give a delightful discovery experience that is able to solve some of these problems for humans as well as for programs. But there are a few other verticals which have not been as easy to solve. Let's look at data quality. Data quality is actually today being solved piecemeal. You're probably an owner, if you're a data practitioner, this probably looks familiar to you. You're probably an owner of a pipeline that transits multiple technologies, multiple different systems. And as you know, you cannot apply data quality in one place. You have to apply it in different places depending on the right spot where you need to be checking things. For example, maybe you're ingesting data from Kafka into Hoodie, or any other open table format, and you want to apply certain kinds of checks, maybe they're null checks or certain kind of schema checks, you'll probably do that in the process that is ingesting that data into the lake. Maybe that's a Flink job, maybe that's a Spark job, whatever it is, you're probably applying that check there. Later on, you might be applying, data set level checks like row counts and things like that. And you might be using something like Grade Expectations or any other open source tool or proprietary tool to have those checks done. And then maybe you load it up into a clean room where you're applying further tests, maybe based on DBT or some other system that you've built. And then finally, for everything that is, an unknown, you might be using an anomaly detection system. So overall, you've got N things that are transiting, and you've got data quality that you're applying at every step of the way. But in aggregate, you don't really have a good sense of what does this data look like, and is it actually trustworthy and ready to use? Because there's nothing that actually stitches it all together for you. Similarly, data management is also a tough problem. If any of you have tried to set up access management for AWS, my heartfelt condolences, because it's a hard problem. There's so many steps, and it takes a lot of work to get even one thing set up. And imagine doing it multiple times. And then there's so many other things in data management that are hard to do. If you want to mask sensitive information, table-based retention, key-based retention, you kind of have to do it separately for every single tool. So how do we solve for this? It seems destined that all of this fragmentation, all of this specialization we have in our data stack requires us to solve these problems piecemeal for each individual system. Well, I think we should be able to solve this by introducing yet another level of interaction. And this is a famous quote by a famous person, and we use it a lot in solving computer science problems in general, right? The way I think about it is you take the modern data stack, which is our entire data stack, and let's say we can postulate the existence of two layers. A layer that gives you visibility into everything that's going on in the stack. And secondly, a layer that allows you to translate logical intent into physical implementation. So perhaps I'm saying, I want all my PII data to only reside in a certain geography. That's a high-level logical statement. And then I can build a system that can translate that logical system into my specific physical stack. Similarly, I might say things like, I only want to care about landing times or SLAs for data assets that are in use. That's a logical statement. And then I can take that and apply it into my stack and say, okay, this means since I'm using Airflow, I need to make sure these Airflow pipelines are always going to land on time, things like that. And so once you have your visibility layer talking to your logical and physical translation layer, then you can actually audit that the translations you're doing are actually happening. And that gives you what I'm calling a control plane. A control plane is something that allows you to assert logical facts or logical intent. It's able to observe what happens, and then it's able to make sure that those things indeed happen. And that's kind of the definition of a control plane, right? It resides above the data plane as a separate entity, and it enforces rules for the data plane. And we have a few examples of this in our own technology space. Not data per se, but in adjacencies around data. You must be familiar with the service mesh. There's a control plane for the service mesh called Istio. A lot of companies use it. It enables fine-grained routing and access control in the service data plane. Terraform, another system that you are probably very familiar with, it allows you to essentially centralize the definition and application of infrastructure properties, policies. So for example, I can say, I want this logical thing to happen. Terraform will plan the change, and then it'll apply it. And I can keep my policy layer neutral, and I don't have to have it be specifically tightly coupled with the cloud I'm running on or the systems I'm running on. And so these two examples give us hope. They tell us that complexity can be tamed. We can have good things. And there are a few things we can also get from them besides hope, which is learnings. We can learn how they have built them, what were the technical capabilities that they have, what are the patterns that they've used. Step one, declarative wins. Always talk about the how, what, not the how. Configuration as code, policy as code, version control, being able to shift left into developer toolkits, all of those things are important. And then finally, as long as you can use adapter patterns and you can adapt to existing technologies, existing APIs, you can get a lot of work done without needing standardization. So with that said, when we take those learnings from other systems and apply them to data, what do you think we should be doing in terms of defining the core capabilities of a successful control plane? First off, breadth. We have to integrate with everything. We need to be able to represent everything. And we need to embrace decentralization, meaning there will be pockets of knowledge in different teams, in different organizations, and we need to be able to allow those pockets of knowledge to exist and then have them connect up into the global truth or the global full view. We need to support low latency. I talked about this multiple times. The system has to support freshness as well as responsiveness. We need to support scale, not just in terms of scale of an organization, but scale in terms of number of assets. And also temporality and versioning is super important. We have to be the source of truth for things that don't exist elsewhere. Logical specifications, when someone says, I want X to happen, that specification has to be source of truth in the control plane. It is the only repository that knows about this logical specification, and it has to act as such. And then finally, goes without saying, every single system or every single change must be auditable. It must be always easy to understand why the system is in its current state and how it got there and who was responsible for getting it there. So these are, in my view, the 5 big things that a control plane should solve for. And let's look at an architecture blueprint for how we do it. So step 1, we talked about visibility being important and breadth being important. And we've kind of seen this already through my early spiel about this data discovery application called DataHub that I was kind of talking about, right? You need a data plane and you need the ability to pull event-oriented signals from that data plane in real time. And you need a metadata graph where you can store this, which is version, which supports time travel, and which supports change subscription. Once you have these 3 things, you can basically answer questions about what exists right now, what existed last week, and how has it changed over time across the whole data plane. And secondly, you also need to solve what's logical to physical translation, and that requires you to be the source of truth for control specifications, which means you need to allow control specifications to exist. You need to allow them to be registered with the control plane. And then on the other side of that registration, you need an operator to exist that can act on that registration, that can basically say things like, a new control specification was registered. Now let me make those changes and apply them to the data plane. And then following that down, that change to the data plane will then get seen by our own metadata graph that can lead us to provide a unified auditing and alerting layer. So you see how we get kind of a full circle now with visibility and then control specifications being registered to the control plane, being applied to the data plane, and then the visibility of that allowing us to get full end-to-end visibility of all of the logical things that we wanted to happen, whether they're actually happening. So this is kind of a high-level architecture picture and a reference flow of how we can build a control plane. Let's talk about a few use cases really quick. First use case, reliable data pipelines. This should come as no surprise. You have so many situations where you've got a data quality tool that is producing results for tables, and there could be multiple tables that are getting ingested. One data quality might be evaluated by the data quality for table A might be evaluated by a data quality tool. Data quality for table B might be evaluated by the ingestion system. All of these data quality signals need to get registered up into the control plane. And then a downstream task, which is trying to run on top of table A and table B, all it needs to do is just check the union of the quality across A and B to decide whether it needs to or it's safe to run or not. This is a common use case that we see in our day-to-day. And this is something that becomes so much simpler to do if you have a control plane like this. Because in the absence of that, that individual task would have to go poll these individual systems to figure out if data is ready and if the systems are the tables are high quality or not. The second use case, building on top of a very simple data quality use case, is quality enforcement. If you're familiar with data contracts, these represent logical specifications for what data should look like. And you could write one of these, register them to the control plane, and on the other side of that control plane, there could be a data contract operator that takes that specification. Perhaps you're saying that a schema of this table should look a certain way, and that data contract operator can turn around and actually make it happen. Now, that might involve provisioning a schema on Kafka, or it might involve provisioning a data copy job that asserts that the schema actually looks the same. It's up to you to decide how you want to enforce a particular contract, but that's where that pluggability of the logic lives. And then on the other side of that, you get that unified audit and reporting as the contracts get run and reported to see that the contract indeed is meeting the data set indeed is meeting its contract, and things are looking good. Similar things can happen with SLA monitoring, and similar things can happen with data access management. So you see the pattern is about the same. You have a logical specification, you register it with the control plane. On the other side of that, there's an operator that spins up and responds to changes, and then takes action and makes those changes actually happen in your individual tools. And if you think about it, a lot of use cases could be tackled with this architecture, whether it's masking sensitive information, table-based retention, key-based retention, all of these things. So you might be wondering, well, this seems kind of easy and hard at the same time. How long is it even going to take to go there? Turns out we're actually not very far. I already talked about DataHub supporting this metadata store that's version-oriented and time-oriented. So that's done. We've got a bunch of signals that are coming out of the data plane. That's done. I mean, of course, with the caveat that done is always almost done, because there's always a new system that comes up, or there's always a new feature. But in the grand scheme of things, we feel like, okay, we're done. We kind of know how to do these things now, and we have good coverage. And a few other things are actually in progress. We've got support for control specifications that is in progress, data products and data contracts. And similarly, we have support for state management that's in the works. And so this gives me a lot of hope that we are, as an industry, actually collaborating on building kind of this deconstructed approach to controlling all of the data that we have and being able to manage it in a cohesive way. Data contracts is a good example. It's something that we started working on earlier this year, and it's now part of the DataHub project. It's a control specification that tells you, here's a bunch of assertions that I want to be true about a data set. Here's a schema, here's an SLA, here's data quality assertions. It's UI-based, but also has a programmatic spec. It's an open source specification. You register it into DataHub, and on the other side of it, a data contract operator can spin up and start doing things. And then it starts reporting those results, and you start seeing it in the discovery experience that this table is meeting its contract or not. So end to end, you've got systems producing monitoring signals, data contract proposals being generated, those getting registered back into the system, and you've got kind of a good end-to-end loop happening where you can start monitoring schema freshness, you can start monitoring schema assertions, freshness assertions, as well as column level quality. So that's just a whirlwind tour of what it takes to build a control plane and some early proof points that these data flows, these control flows are actually coming to life. But the reality is the data stack continues to be highly fragmented. And I believe a metadata-driven control plane holds the key to bringing order to it. We're working on it together with the whole community, and we would love to have all of you participate. We really think data quality, data governance, data management, all of these somewhat disparate disciplines can be harmonized if we solve it in this kind of uniform way. So join us, help us build the control plane of data. I think it'll help the whole industry if we had something like this. We are available on Slack on slack.datahubproject.io, or you can always find Acryl on acryldata.io. And if you want to actually join us, we also have a careers page. So please show up. We advance the open source DataHub project and also work on Acryl Cloud. So it's fun times, and really happy to be here and looking forward to hearing the other talks.